All right, question 1 reads, and we're going to do this together, and I don't have the mark scheme in front of me, but we will mark this at the end. And if we, if you see me going down a wrong path, or if you've got some insight, if you're like, wait a minute, I think this, okay, please don't hesitate to offer that discussion. That's the best thing that we can really do, is kind of brainstorm together and kind of think through this. Because then, as you address similar questions, other papers, it's like you've got different ways to sort of attack it, because, oh, that's the way that, so-and-so suggested, and that actually is helpful here. You'll find that there's always more than one path, typically, to arrive at the correct solution. We'll see that. All right, a student creates a table to show reasonable estimates of some physical quantities. Which row is not a reasonable estimate? And you can actually point to language in the syllabus about, students will be able to make reasonable estimates of physical quantities, throughout the physics syllabus. So we have the current in a fan heater, 12 amps, the mass of an adult person, 70 kilos, the speed of an Olympic sprint runner, 10 meters per second, and water pressure at the bottom of a garden pond, 10 to the 6 Pascal. Which is not a reasonable estimate. Anybody have any ideas about this, or anybody want to make a guess? Yeah. I don't know. I really don't know the answer to this one. I think it's either A or D. I mean, A, it's like, that seems like a high current, but maybe it could be, 12 amps. That seems kind of high. I would say to really nail it down, I mean, this seems very reasonable. Okay, 70 kilos. All right, I'm 100 kilos, but I'm a tall person. Speed of an Olympic sprint runner. We could convert this to like miles per hour. Okay, remember how to do that? Multiply it by my birthday, 2.23, 10 times 2.23, 22.3, 20 miles per hour. I mean, it's an Olympic sprint runner, so it seems kind of fast, but it's like, yeah, 20 miles per hour for a little bit, humans can run. So I think that these two are reasonable. We could maybe do a calculation here and see if, if it's there. And so let's remember, and maybe we don't even need to remember. Is there some kind of an equation that's helpful in solving this? And it's that one, hydrostatic pressure. So pressure is rho GH. So think about that. The pressure here, P, is the density times G times H. So really what you could do is make an estimate about what is the height of a pond. It does say water pressure. So I was, going to sort of go to this one because atmospheric pressure is what, 101 kilopascals. And so you already have like that much pressure from the atmosphere. And at the bottom of a garden pond, you've got the pressure of all the atmosphere plus the water. But the way they've worded it, it's like, well, what's the water pressure? So I think we can neglect like the 10 to the 6, pascals of air pressure that's above the pond. And so, would the sort of pressure of all the air above the pond equal like the pressure of just the water in the pond? Is really kind of what this question is saying, because you might remember from chemistry this value.
Teachers and students, please pardon the interruption, but please send those students that are on the FA list to the auditorium. If they are in front of you and not testing, please send them to the auditorium. And I sent this list to you again just a few minutes ago. Thank you.
That's what somebody needs to do, an edit of all like the YouTube videos where I'm going through a lesson and it's like, pardon this interruption, pardon this. And then like sometimes I'm just like, just fall down on the chalkboard. All right. The people that are on the FA list, guess where they are? Accent. 101 kilopascals. So that's what, 10 to the 5. Okay, right? Because it's 2 orders of magnitude here, and kilos 10 to the 3. So there's actually like 1 by 10 to the 5 pascals of atmospheric pressure. Water pressure at the bottom of a garden pond, 10 to the 6, another order of magnitude. The density of water is 1,000 kilograms per cubic meter. Okay, so that's something that you can commit to memory. I think in any question where you kind of really need to know it, this one I guess you kind of do. They probably give it to you. So 1,000 kilograms per cubic meter. And then on Earth, 9.81 newtons per kilogram. And, you know, what's a garden pond? How high would you say that is? Maybe 1 meter, 2 meters, maybe? I don't know. 1.5.
I would assume like, when this is garden pond, I would think like something small.
I'm just going to say 1.5 meters here. And the idea is that like it should be very well off, you know, like an order of magnitude off, you know, if it's this answer. Because yeah, you know, some garden ponds are going to be deeper than others. I'm still, you know, 12 amps. You know. Maybe that is reasonable. All right, so what does this work out to be here? Times 9.81 times 1.5. So it's like 14,715. That's the water pressure. You know, it's you know, it's off by a few orders of magnitude. And even if you add it in, you know, the atmospheric pressure, like you say, hey, well, the water pressure at the bottom of the garden pond, you know, if you put a pressure sensor, it's feeling all the water pressure, but that water is also being pressurized by the atmosphere above it, you know? So it's like, how do you interpret this? You know, in any way that you do it, it seems like D sort of is the answer. And so, you know, I'm gonna go with D here. Now at this point, you could say, I don't know, I like A, or B or C. You know, it's really up to you. Okay, you pick the answer that you feel best about. We'll give ourselves feedback at the end of it. I'm going to put my best answers down. So like if you sort of, you know, like how deep would we have to make this in order for it to be, you know, valid? And then you could say, well, that's not really a garden pond. That's Lake Baikal in, you know, Russia, the deepest lake on planet Earth. Something like that. Very beautiful. This symbol here is somehow an artifact of the printing. It should be, I think, a degree symbol, like through which angle. So this little gamma, that's a degree, that's a little circle. All right, question 2, moving right along here. A particle travels in a straight line with speed v. The particle slows down and changes direction. The new speed of the particle is v over 2. The new velocity has a component of v over 4 in the same direction as the initial path of the particle. Through which angle has the particle turned? That sounds like the kind of one you want to draw a picture for, right? Particle travels in a straight line with speed v. The particle slows down and changes direction. The new speed of the particle is v over 2. So particle's going like this, changes direction, okay? The new speed of the particle is half of the original velocity. So this thing has speed v, and now this thing has v over 2, but it says the new velocity, and remember, this is the difference between the scalar speed and the vector velocity. The new velocity has a component that is 1/4 of the initial velocity in the same direction as the initial path. So it's like if this is the initial path, then there's a component of this new sort of vector, and so let's just say it's like this one. There's a component of it in the same direction here that is 1/4 of this velocity. All right, and you might draw this differently than I have, you know, that makes more sense. I probably need to translate this to a more sort of sensible mathematical figure here. I'm saying like, okay, it's moving along, it changes directions, it's got some new direction, and now it's got a new vector with components like I made it down, you could have made it turn up. But it's got components now down and to the right, for this new vector here, this hypotenuse. And we know that the initial velocity v, the initial speed v rather, is related to this component here, v over 4. Through which angle has the particle turned? All right. So this is our right angle. This is the angle through which we've turned. The hypotenuse, right, is v over 2, right? Because it says its new speed is v over 2. So I think we want this angle right here, right? And so we've got the hypotenuse, and we've got the side opposite from that angle. So opposite hypotenuse, that's the sine function. So could we say the sine of this angle that we care about, call it theta, this is the typical physics sense, is equal to the side opposite, which would be v over 4, over the side that is the hypotenuse, which is v over 2. And then we can rewrite that as 2v over 4v, which cancels the v's. The sine of what angle is a half? Isn't that 30? Hold on a second. So I've just solved for this angle here, 30. And in your question or your comment is what?
If you look, so the v over 2 is going at the angle. The other one is going straight down. That's not.
This one here?
Yeah. You need to find the one that's going to this side.
You saying we want this angle?
No. Like,
Are you talking about the angle in the same triangle,
Yeah, well,
on the
that-
lower?
yeah, like it would be the. Trying to think how to.
All right, so let me walk through it again, and as I'm talking through, you can say, okay, well, right there. Okay. So we got a particle that's going to v. So far, so good. The particle travels in a straight line, speed v. The particle slows down and changes direction. The new speed of the particle is v over 2. So like this is its speed right here, v over 2. The new velocity, okay, so the speed of this is v over 2. The velocity has a component, v over 4. Okay, so, okay, I see what you're saying. If this is the velocity vector here, okay, like it changes direction, it's actually moving along this path, right? It has a component, v over 4 in the same direction as the initial path, and so that's this sort of angle here.
Yeah, can't you just use cos instead, because that's adjacent over hypotenuse?
But do we want this component, this downward component?
No, you don't. Well, so the v, it's still going to the right, and then it cuts off down. So the way I'm looking at it is like flip the triangle over the hypotenuse. So like you still, so you still have the v over 4 going in that direction.
So he still has a component, v over 4 going this way, but turn, sort of in this direction.
Yeah. So the angle it turns is that.
Is this angle here,
Right, yeah.
which I think is the same as this angle here. It's just a matter of like when you turn, okay, you're turning through which angle? Are you turning through this angle here? So like if we change direction, okay, and we go like this way. Well, now there is no component in the same direction. So we know we didn't turn that much, right? We didn't do a 90-degree turn. So it's like that right there. If we were to sort of go this way, then it's like this is the angle of our turn, right? Do you turn 270 degrees, or is this a 90-degree turn? You're just turning 90, right? You're going this way, and then you turn to the right. That's a 90-degree turn. So if this thing is going this way, and it turns like this, okay, then yeah, it is this angle, right? Like that's the angle through which you turn. This angle is the angle through which you turn. So it'd be 30 here. So this is 90, this is 30.
I just used the cos function in my calculator. I came with an angle of 99 degrees.
Look at our choices. Okay.
Like, here, let me render you that, because it's inverse the sine of v over 4 over v over 2.
That's kind of what I was thinking, like a complementary angle. Like if this angle here is the same as this angle here, and this is a 90-degree angle, and we just solved this as 30, then like, okay, we turn through this 60 degrees is the same thing as like this. It's like you almost have to like stand up. It's like, okay, I'm a particle with speed v, and I'm turning like this. I'm turning through this angle here, right? I think it is 60.
I got 60 as well. I'm sure I hit the second on my calculator.
Anybody else have any thoughts on this? What do you think is the best answer here? Anybody out there? I think it might be 60. So we calculate 30. Nothing wrong with this calculation using the sine function if you're sort of looking at a triangle and going, okay, I know, sort of I want to know this angle, even if it's not sort of the answer to the question. You say, well, I can figure this out because I've drawn something that's sort of it makes sense with what they've listed. This is the initial velocity, here's a component of it. And yeah, you could have just kept it up here, like, okay, it maintains this same component. So now there is a component going down. The speed of it, okay, it's actually going v over 2. So that is the hypotenuse, right? I don't think there's any flaw in that thinking. So if we kind of maybe clean this up a bit instead, here's the thing going v, here's a component of it, v over 4. There's a component of it going down, so that's the new thing. It turned through this angle. Yeah. So you can kind of just clean it up like that. It was going speed v. It maintains a component v over 4. It turns through this angle. Here's its new sort of trajectory. It's got a component that's going down, but we don't really care about that. We know that the speed of this thing is v over 2. And if you're solving for this, you say adjacent hypotenuse. So the cosine function would solve it directly. The sine of theta minus, 90 minus theta is the same thing. It's the cosine, right? So I think D for this one, right? Because if you use the cosine there, you just get the complement of the angle. And yeah, you could solve it sort of this way too. Like I just basically initially set it up with this triangle here and solve for that angle, right? Which is the complement of this, the angle through which you turn. Give ourselves feedback at the end and see if we need to revisit this one and go, oh, boy, that was a little tricky there. Yeah, you have something else that we did wrong.
No. Do you want me to tell you what I think is the best answer based on looking at the mark scheme?
Yeah.
It is D.
Okay. Yeah, if you've got the mark scheme in front of you, then maybe we can do that, give ourselves immediate feedback. I was going to wait till the end of this, but how about one up here? You got that in front of you too? That's one way to solve it. It's like, I got a good way to solve this here.
Yeah, that was also D.
D, this one's going to be C. Because it's always C. Well, 25% of the time it's C. Not always. All right, the speed V of a liquid leaving a tube depends on the change in pressure delta P and the density rho of the liquid. The speed is given by the equation V equals K times the quantity delta P over rho to the nth power, where K is a constant and has no units. What is the value of N? Start on the left side, give yourself some meters per second velocity units. K, we don't even care about K. It has no units. What are the units of pressure though? We could think about pascals of pressure, like this guy up here. But what is a pascal? If pressure is force per area, then a pascal is a Newton per meter squared. So I'm just going to start writing Newton per meter squared. I got density down here, which is kilograms per cubic meter, right? Density is mass per volume. Those meters cancel out 2 of those. This Newton, you may recall, is a kilogram meter per second squared, right? So a Newton is a derived unit. It is an SI unit of force, but it's not a base unit. You use F equals ma. M is kilograms, A is meters per second squared. So this Newton is really all of this. I still had a meter up there. In other words, not all of these cubic meters from the density canceled, right? I still have one of them, so that's meters squared. And I still have this kilogram down here. So that kilogram is going to cancel that one. And if I'm comparing the left side of this equation, meters per second, to what I have left on the right side now, so remember, like this, I kind of rewrote all of this over here. So I have meters squared per second squared. And so you say, well, what do I need to do? To what power do I raise something that is meters squared per second squared to make it meters per second? So it's like we need to take a square root, right? Taking a square root is the same thing as raising it to the 1/2 power. So choice A seems very reasonable here, and that's all it takes for that. It seems, a little bit tougher when you look at the equation, but once you kind of see what cancels, you're like, oh, meters per second, like I see it on both sides, right? It's just sort of how do I get rid of those squares? Question 4 reads, the values of displacement, velocity, and acceleration of a vehicle can be deduced from graphs representing its motion. Often the areas under these graphs or the gradients of these graphs are used. What would not give a value for a displacement, a velocity, or an acceleration? This is a great type of question as you do these previous papers for problem studies, because the incorrect answers, also sort of give you some insight into sort of the physics here. So if we just sort of go through each one and say the area under a velocity time graph, that gives displacement. The units are really sort of the key to it all. An area problem is like length times width, right? We're multiplying the x and the y axes. So if you plot, velocity against time, and you think about the units, it's meters per second of velocity times seconds of time. So you have meters per second. If it's an area, remember you're multiplying it by. So meters per second times seconds, the seconds cancels, and I'm left with meters of displacement. So the area underneath the VT curve gives displacement. The gradient of a displacement time graph, well, that's velocity, right? And again, if you're doing gradient, that's rise over run, so that's a division. So this is a multiplication problem, right, an integral. This is a division problem, derivative. So again, you can do the same thing. You can just sort of construct a quick displacement time graph. So that's meters of displacement, seconds of time. If you did rise in meters, over run, you have meters per second, which are units of velocity. The gradient of a velocity time graph, as if we took the gradient of this graph over here, it'd be meters per seconds, or meters per second squared, and those are units of acceleration. The gradient of an acceleration time graph is called it's not displacement, velocity, or acceleration, it's called jerk. Okay. So the rate of change of acceleration is jerk. And so that's the correct answer because they don't ask us about that. And that is important, like satellites have to deal with sort of, the rate of change of their acceleration. Think about if you drive and you accelerate sort of uniformly by like just gently pushing the gas pedal, that's an okay way to drive. It's not very, sort of jerky. But if you constantly change the direction of your motion, okay, with your third accelerator, so you have 3 accelerators in a car, right? You got your gas pedal that speeds you up, you got the brake pedal that slows you down. Both of those are types of acceleration, but you have a direction changer, your steering wheel, okay? And so that's an accelerator too, right? Every time you move the steering wheel, you're accelerating your car. And so just imagine if you like to drive, sometimes like I do on my way home, there's like a parking lot I can cut through. And sometimes I just like, swerving all around the parking lot there on my way home. It's kind of fun. No one's in there, but I can sort of cut, across some traffic there. But, you're sort of moving the car back and forth. It's very important. Question 5. A ball is released from rest above a hard horizontal surface. The graph shows how the velocity of the bouncing ball varies with time. At which point on the graph does the ball reach its maximum height after the first bounce? I think we did this question before.
Yeah, we did.
Does anybody remember the answer or can think through it again even better? So it's tough to sort of translate what is a velocity time graph into like motion, right? You have to really think about the ball is released from rest above. So it's going 0 initially because we release it, we drop it, but then it picks up speed, okay? It's increasing its velocity. If we were to take the slope of this, I bet you the slope of this line would be 9.8, 9.81 meters per second per second. So like if this is 1 second, then that would be 9.8. It's picked up 9.8 because it's probably just falling on Earth, right? And then at this point, it rapidly changes its velocity. Like it slows down to 0, and then it has a negative velocity. What's a negative velocity? Yeah, so they're sort of assigning the downward direction as positive, right? And so here it's going, it's turned around, it's going back up. Okay. So it has negative velocity here, but then the velocity goes back to 0. Okay. And then becomes positive again. So this is the moment when the ball sort of, you know, is still moving down, and then the floor, right, the surface sort of changes its direction, but it's still in contact with it. And now it leaves the surface, okay, with the maximum sort of negative value, right? Like let's say it leaves the, you know, it's picked up some speed here, and then it almost looks like this distance is about the same as that, maybe just a little bit smaller. So if you want to like really use this again as a problem study to like, this is what bouncing looks like. Okay, this is a bouncy ball or somebody on a trampoline, all right? And you say, well, what really is going on sort of in the motion here? You could, you know, assign values if you wanted to. You can think about energy in terms of like the height of these velocities above and below really shows the energy losses in the bounce, right? Like as they get, see how it is getting smaller. And that's what's happening with the bouncy ball, right? Like there's some energy losses along the way. It doesn't just stay as kinetic energy in the bouncy ball, but the floor itself, right? The surface is going to be shaking more. The atoms in it are hotter, and that costs energy. And it comes from the organized potential energy of all the, you know, molecules in this ball falling down together and slamming into, you know, a surface. So that energy stays in the universe, but it doesn't stay in the ball. So at this moment, right, it's got sort of maximum negative velocity, and that means upward velocity. So that's the moment it leaves the surface, okay? And then gravity does what? Slows it down, slows it down, slows it down until it's 0. Well, why would it be 0? Because it's at the top of its flight, right? Because then it goes positive again. Remember what positive is, it's falling, right? Here the ball is falling, like down is positive, right? So here it's falling again. So at point C, that's when it's at its maximum height, and that's, I think, what it asks us for. And then it starts, you know, falling down again. And then at point D is its second bounce. So it's like it's falling, bounces, gets to the top of its flight. And see, it's tough, I think, for our brains to like look at this and go, okay, it's turned around and changed its direction here, but yet this is just a constant line like that. And that's because that's what acceleration is. It's just a constant accelerator, right? It's slowing down this negative velocity to 0, and it keeps on. This is like when students say, oh, well, the acceleration of a projectile goes to 0 at the top. No, the accelerator is constant, it's gravity. The velocity goes to 0 at the top. The gravity keeps acting on it, right? If it didn't, the ball would just float there, you know, or fly into outer space. So I think that's the sort of thing that's a little bit tougher for our sort of brains to get used to, is like, we're not looking at position or displacement, we're looking at velocity, right? And so like the slope of this is the acceleration. So it slows it, you know, slows it down, speeds it up. Okay. So C, right? That would be when it's at maximum height after the first bounce. A ball is kicked upwards at an angle of 45 gamma, that's degrees. I don't know if the printer does that. Like if you were to queue up this paper, that's not a typo on the paper, but for some reason when this gets sent to the printer, they're like, we can't print a circle, you know, make it a gamma. After a short flight, the ball returns to the ground. Then maybe assume that air resistance is negligible. What is never 0 during the flight of the ball? See, that's like kind of what I was talking about here. Like it's such a misconception that they assess students' knowledge of it all the time. So sometimes it'll be worded this way and the answer will be acceleration, but that's the answer here. You know, acceleration is never 0 because it's a constant sort of gravitational force, but I don't know, let's read through these all. the horizontal component of the ball's acceleration. Air resistance is negligible. All right, so we're looking for the one that never goes to zero, so it's always a non-zero value. The horizontal component of the ball's acceleration, the horizontal component of the ball's velocity, the vertical component of the ball's momentum, the vertical component of the ball's velocity. So let me draw a quick picture there. Ball goes up, falls back down. Let's start, at the end, work our way up here, see if we can't disprove or prove one of these. The vertical component of the ball's velocity. So if it's kicked upwards at an angle of 45 degrees, it does have an initial upward component. The vertical component of the ball's velocity will go to zero at this point though, right? At the top of its flight, the vertical component goes to zero. So D can't be right, it does go to zero. The vertical component of the ball's momentum, likewise, if it still has mass at the top, but if it has zero velocity in that direction, and all we care about is the vertical component, then that also goes to zero. At the same moment that this went to zero, so did its momentum in the vertical direction. How about the horizontal component of the ball's velocity? Well, that's still moving sideways. That's why I can keep moving this way. So it's the vertical component that goes to zero, not the horizontal component of the ball's velocity. That stays constant all throughout when air resistance is negligible. So the horizontal component of the ball's acceleration, that must go to zero because the other ones we've sort of disproven. So let's sort of think through that. How does the horizontal component of the ball's acceleration become zero? Well, I suppose the moment that you kick it, okay, it goes from rest to whatever, it's going to have. But then after that, it's just a constant Vx, right? That's why we use Vxt. We don't use U, the initial component of X. We use V because it doesn't change, right? It's only like the initial component of the Y that changes. So A is the correct answer here, I'm pretty sure. It says, what is never zero? The vertical component of the ball's velocity. Oh, yeah. The horizontal component of the ball's velocity is never zero. That's right. So it stays this way. And so I guess, to say a ball is kicked, so this has to be part of it. I was thinking like after you've kicked it, not that everybody. After you've kicked it, like there's nothing to sort of, change that. If air resistance is not negligible, then there's also an acceleration in that direction. So when we study projectile motion, we're usually, there's a constant X component and we apply acceleration, the equations of motion to the Y direction. But then later on in the year, they talk about the drag force. And so, that can sort of be affected. So I guess, I just sort of interpreted that. The horizontal component of the ball's velocity is never zero, right? Because it's constant here and it's not here. But then, okay, a ball is kicked. A ball is stationary and then it is kicked. It is kicked. We got to sort of start it then. So B is correct. My bad. Thanks, David, for catching that mistake. Number 7 says the mass of a rocket-propelled truck. That just sounds awesome. A rocket-propelled truck, all right, it's approximately equal to the mass of the fuel in its tank. All right, so the truck is basically negligible. It's just the mass of the rocket-propelled truck is about just the mass of the fuel in its tank. The fuel is ignited and the truck is propelled along horizontal tracks by a constant force. The effective air resistance is negligible. During a test run, the fuel is consumed at a constant rate. Which statement describes the acceleration of the truck during the test run? Be careful as you think through these. This is, I think, maybe a little bit of a trickier question. The acceleration of the truck decreases as fuel is consumed. The acceleration of the truck increases as fuel is consumed. The acceleration of the truck remains constant, or the acceleration of the truck is 0 and the truck moves at a constant velocity. Be careful to sort of say constant force, constant acceleration, because F equals ma, because you're not really considering then this. You're just saying with a constant force, there must be constant acceleration. It's a reasonable thing to sort of think through, because we kind of think about like with projectiles, right? Like there's a constant accelerator, constant force acting on it, you know, that all makes sense. But the fuel is ignited, okay? So what does that mean is happening? Especially because the mass of this rocket propelled truck is basically just the fuel. Like the truck is negligible compared to the fuel tank. And so we ignite the fuel, what's gonna happen to M? Yeah, M decreases. So like this is a rocket, you know, where most of the rocket stays behind here on Earth, okay, in terms of exhaust gases. We get a little bit of the mass of the rocket up into outer space at the expense of leaving most everything behind. You know, as Tars so astutely pointed out in Interstellar. The only way human beings have figured out how to get anywhere is leaving something else behind. So if this is going to go down and there is a constant force, this is fixed. In order to keep this force constant, the acceleration is going to have to increase. All right, so it's going to be B. Good. An object is dropped at time t equals 0 from a high building. Air resistance is significant. Now they tell us it's significant. 3 graphs are plotted against time. The height of the object above the ground, the speed of the object, and the magnitude of the resultant force on the object. What are the quantities x, y, and z? And then we've got some tables here to sort of entertain. Let me zoom out a bit to get that whole problem there. All right, so you can kind of see each of these graphs. And remember, what we're looking at is the height of the object above the ground as a function of time, the speed of the object as a function of time, and then the magnitude of the resultant force on the object as a function of time. William, I saw your hand up a moment ago. Did you have a comment on this or a way forward on it or a question?
Yeah, I was thinking it was B.
D, you already got to the answer?
B.
B? All right.
Yeah.
All right, let's think through here. The first thing that I actually thought about was like, this looks kind of familiar. You know, so when air resistance is significant, remember things are going to reach terminal velocity. So I think this one has to be the speed of the object. So the first thing I would hone in on is that Z is likely the speed of the object. And so, yeah, I think that's, you know, I would eliminate A and D. And I kind of think about it like with a test taking strategy of, you know, if I can right away eliminate 2 answers and get it down to a 50-50, then throughout the test, I'm sort of in better shape. Because if I have to, you know, guess between, you know, 2, if I can't, you know, figure out the rest, then at least I've, you know, hedged my bets, and, you know, it's not a 25%, like a 50%.
That's kind of what I did. And then just looking at the graph where comparing it to X, the top one, the height of the object is going to decrease rapidly as time goes on, so eventually hit 0. It's going to make sense for X to be height of the ground.
Yeah, the thing that I really hone in on with X and Y is that one quantity goes to 0 and the other one never reaches 0. And if Z is correct, that this thing reaches terminal velocity, what can we say about something with constant velocity in terms of its acceleration? Acceleration is 0, so the force is 0. So I'd be looking for, again, I go right to the familiar thing. This is terminal velocity. I know something about that. Terminal velocity means the forces are balanced. The weight, which is causing this initial acceleration, has been balanced by the drag force by this significant air resistance, right? And that can only be true when the resultant force goes to 0. That's F equals ma. So if A is 0, F is 0. And so I want X to be the magnitude of the resultant force. Choice C. Then does it make sense that this curve could be the height of the object above the ground? Sure. Right? It never tells us it hits the ground. So it's getting there, right? And it's decreasing like this, not at like a constant, okay, because there is that force. So it does that. Wow. Yeah, I mean, I'm going to go with C on this one. Question 9. A student attempts to find the density, rho, of aluminum. Aluminum? Aluminium. Okay. Aluminium. By taking measurements of a rectangular sheet. Then you got the mass, the length, the width, and the thickness. He uses the equation rho equals m over WLT. I mean, WLT. How do you like, oh, calculate the volume? It's width times length times thickness. What's up with length times width times height? You know, anyway. What is the calculated value of density with its uncertainty? And we've come to the essential question of the day, right? Kind of uncertainties, and sometimes we'll get questions like this. All right, so I've done enough of these that it's like, that's kind of dull for me. And I want to see if I can't just figure out the answer by looking at the answer choices and going, oh, I bet you it's this one. So I'm going to work on that. And you guys like do the actual physics, okay? And I'll come back and help you, you know, with that if you get stuck. No, there's actually no way forward there. You got to do the math. I think there's a way to like be clever with the answer. All right. So the first thing I would do is actually just you know, calculate it based on who. Don't worry about the uncertainties. Just calculate it with the values. So it's going to be 51. And look at the units too. Everything is grams per cubic centimeter. The only thing we need to convert is this one. Okay. Be mindful of the thicknesses in millimeters. So to get cubic centimeters, you can't plug in 0.2. But this you can't plug it in grams. And again, we don't worry about the uncertainties yet. So the first thing I would do here is actually just make this centimeters. So if I have 0.2 millimeters, there are 10 millimeters per centimeter. So 0.2 becomes like 0.02. So this is really 0.02 plus or minus 0.001 centimeters. And now I can just calculate 51.6 divided by, I'll do it the way that they put it. The width, 10, the length, 100, the thickness, I just calculated to be 0.02. So I'm dividing by something smaller, so I'm going to say it's D now. This is my guess. Okay, I still want to do the calculation, but I'm going to jump ahead to D. I'll tell you why in a moment. So you do get 2.58, and so yeah, it's 2.6. And now we got to think about, is it plus or minus 0.1 or plus or minus 0.2? And so here we can, anytime you're multiplying or dividing values, the rule is to add their percentage uncertainties. You add the percent uncertainty. So we have uncertainty in mass and in, you know, all of them. How do we determine the percent uncertainty if we're given the absolute uncertainty? So remember, this is the measured value plus or minus the absolute uncertainty. So it's always the absolute uncertainty divided by the measured value. And this will give us the percent uncertainty. So we do that for all of them. 0.1 divided by 51.6 times 100. So this one is contributing like 0.2%. This one here, 0.1 divided by 100. 100. That's another 0.1%. 0.1 over 10. So this one's like 1%. And the thickness. Now you can, keep the way you can use the centimeters, or you can use the millimeters just as long as you're consistent, because it's just a ratio anyway. So 0.01 divided by 0.2. 5% uncertainty in that. So there's 6.3% uncertainty in this calculated value. You have to account for all of the uncertainties in a calculated value like that. So I can then take my 2.58 times 0.063, and that is 2.58 plus or minus 0.16254. And then you kind of say, well, I know this, if my uncertainty is here in the 10th place, then I'm really only certain to that point. And so that sort of governs where you round it to. You'd say, I must be 2.6, right? I can't report it to this precision because my uncertainty is in the 10th place. So it's 2.6. And then you round this up, right? So this is greater than 5, so it rounds up to 0.2. So my uncertainty is in the 10th place, but it rounds up, not down. So it's not 0.1, it's 0.2. And so I was correct in jumping ahead to D, at least if this is correct. And I could just see like, okay, why are these answers here? Because many students will forget to convert this. And so if they just leave it like that, it's going to be a bigger number here, and they're dividing by a bigger number, it's going to be smaller. So these answers are designed to capture the students that forget to convert millimeters to centimeters. So as soon as I sort of recognized, oh, that's really the trick in this question, these answers can't be right. They're the ones that are going to get those students that don't do the conversion from millimeters to centimeters. Everything is cubic centimeters. And then I just assumed that it would be greater uncertainty because there were so many values, that were involved in it, that I was just sort of thinking, well, it's probably going to be the higher one. And so that's why I sort of jumped ahead to D. As soon as I put this value down here, I kind of knew that we would get to D. But it's still worth it to crunch the numbers, and especially, to explain to students that need to understand that. So it's like, if I'm taking the test and I got, 75 minutes, maybe at that point I really would just fit D and just kind of move on. I wouldn't bother with all this. The graph shows how the momentum of a motorcycle changes with time. I think I mentioned the other day how the momentum of a motorcycle can change very, very quickly. Okay, if you crash into the trunk of a car with it. The momentum of the motorcycle will change, but the passenger is an object in motion, which will remain in motion until some outside force stops that passenger. Remember that. You can't break those laws of physics, only your bones. What is the resultant force on the motorcycle? Anybody know how to solve that from this? Yeah.
And then just take the 5,000 and divide by 10, because that'll be newtons.
Yeah. You could think about it like this. Force is the rate of change of momentum. And so if you're given a change in momentum over a change in time, it's the slope of that, right? Rise over run. So we're rising 5,000, we're running 10, 500 newtons of average resultant force. We'll go back there. Question 11 reads, a particle with mass and charge is moving from left to right in a uniform gravitational field and a uniform electric field. The gravitational field is downwards. The gravitational force and the electric force on this particle act in opposite directions. What could be the sign on the charge of the particle and the direction of the electric field? Okay. We got a particle here, and it's in a gravity field that we know is like going down. Okay, that's the gravity field. But how about the electric field? Well, if the electric force acts in opposite directions, then it's going to act up, right? Because like gravity goes down. What could be the sign on the charge, sign of the charge on the particle, and the direction of the electric field? Okay, so let's kind of go through each one. If the sign on this thing is negative and the field were down, well, if the field is down, okay, then that's the way a proton moves. So an electron would move upwards, and an electron is negative. And so I think that's it, right? A. That seems reasonable. If the electric field is also pointing down, right, then remember, electric fields are governed by how a proton moves. But electrons move the opposite way. So the electron would move up with a force upward, and electrons are negative. So I like A right away. And then you could kind of go through the other ones and say, well, that won't work. But as soon as you get the right answer, might as well move on to the next one. Sometimes you're sort of cautious about that because, like, really, was it the first one, or did I just, would they all be right, some way? Like, if I did the next one, would that one sort of be incorrect? And so if you did, if you said, well, if the direction of this field were up, that's the way a proton would move. But if it were a negatively charged, particle, it would go down, and then this wouldn't be true anymore, where it says the gravitational force and the electric force act in opposite directions, right? We know the field is down for the gravity field. And then the direction of the electric field left and right, that just kind of doesn't make any sense for opposing gravity. So, yeah, got an A. A sphere is acted upon by various forces, all of the same magnitude. Which system of forces provides a resultant torque, but zero resultant force on the sphere? I heard D. Anybody else have one? But zero resultant force.
But that would have been torque.
Yeah, we need a torque.
I thought it was C at first glance as well. Well, then on A and B, wouldn't there be upward? Wouldn't there be, from this perspective, wouldn't there be upward force because it's two upward vectors?
Yeah, I mean, you got both of these going up and then this guy going down. So you might say, well, this might be reasonable, but is there any torque here? So I think this might satisfy this condition, but not this one. Here, it's like these two forces seem to cancel each other out. And so you'd be pulling up just sort of on one side here. This one is, no resultant force, but again, no torque. So between B and D, if you pulled down on this one and pulled up here, yeah, that's kind of a tricky one. Does anybody have any sort of clear insight into this? Or like, the way I think about it is this, and that's why I'm really, sort of leaning towards this one here. Because I really, I'm kind of, yeah.
It's saying that all the vector or arrows, they're all equal in magnitude.
Oh, yeah, yep.
So because there's more upward on B, since there's more upward vectors on A and B, would that make it go? I'm thinking of it that it makes it go upward, so that they all be, if there's going to be no resultant force.
Yeah, you're right. A moment ago when I said, it's possible that this could be true, I was sort of neglecting this information. So that's a good point, right? They're all the same magnitude. So it's not like this could be twice as strong as these. They kind of look that way in my eyes, but it could be like an optical illusion because these are, connected to the side here. So like that's part of the vector too. So they look like short. But yeah, so like there's more ups than downs. So the resultant force, more ups than downs.
So the bare minimum would have to be C or D, but there's going to be no torque on C because it's just two pulling on the same side of the object.
That sounds pretty good to me. So D. We'll go with that. A uniform horizontal footbridge is 12 meters long and weighs 4,000 newtons. It rests on two supports X and Y as shown, a man of weight 600 newtons is a distance of 4 meters from support X. What is the upward force on the footbridge from support X? All right, so let's put some info here. Sorry, let me check. Yes is the answer to the question that the viewer posed. All right, so here we've got 4,000 newtons, and this right here would be 6 meters from here. This is 4,000 newtons. Okay. I kind of think about it like this. You got 600 newtons, that is 8 meters away from support Y. You got 4,000 newtons that are 6 meters away from support Y. And each of these would be moments that would make the footbridge turn this way, anti-clockwise. And the only thing that could provide a clockwise moment, okay, would be this. Up, right, this way. So the support here, the upward force on support X, okay, is going to be the clockwise moment equal to the sum of these anti-clockwise moments. So that's sort of just the thinking, okay? And now let's sort of crunch the numbers. And so what are the sum of these anti-clockwise moments? It's going to be the distance 6 meters times 4,000 newtons plus the distance 8 meters times 600 newtons to account for both the moment of force from the footbridge itself, which is 6 meters because it's uniform, that's half of its total length. And we're told that he's 4 meters away from here, so it means he's 8 meters away from this pivot, right? We can take moments about any pivot that's convenient. 6 times 4,000, 24,000 Newton meters. 600 times 8, 4,800. 28,800 Newton meters of moment that also must be acting clockwise. That must be also acting clockwise 12 meters away. So I just sort of say, well, these are the sum of the anti-clockwise moments, and I'm going to equate it to the sum of the clockwise moments, force times distance. The distance there is all 12 meters away. So it's just taking this and dividing it by 12 meters. And get the force equal to this number divided by 12. The units cancel. Meters, and we get 2,400 newtons, choice C. That's moment of force. And again, with the equations in mind and the ideas in mind, that's pretty straightforward. You know, you don't have to, you know, everything's given in nice friendly units, no conversions. It's really just saying, do you know the principle of moments? You know, and you're able to sort of take moments about a pivot and find sort of the right pivot to do it. A metal block has a mass of 750 grams. 60% of the mass is magnesium and the remainder is copper. The density of magnesium is 1.7 grams per cubic centimeter. The density of copper is 9 grams per cubic centimeter. What is the density of the block? I'm always hesitant to solve something like trying to factor in a percentage of it. That's, you know, it's like I want to sort of break apart the metal block into its magnesium and copper constituents and then sort of like put it back together again. So This metal block is 750 grams, 60% of the mass. So of this mass, so much of it is magnesium. And so like right away, that's what I want to find out. 450 grams of magnesium, which means 300 grams are copper. Okay, like that, that's what I've got here. The density of magnesium, okay, is 1.7 grams per cubic centimeter. The density of copper is 9 grams per cubic centimeter. What is the density of this block? So these densities coupled with these masses allow me to calculate their respective volume. Okay. Once I know each of their volume, I could say, well, the volume of the metal block would just be the sum of them. And I know the mass of the metal block. So mass divided by the sum of these volumes gives me the density. So that's the roadmap. All right. How do we turn density and mass into volume? Just let the words take care of you. You take care of the words and they'll take care of you. Okay. Let's write down what we're given. 450 grams. I don't want to be in grams, I want to be in cubic centimeters. And I know for this magnesium that for every 1.7 grams, I've got 1 cubic centimeter, right? Because that's what the density tells me, how many grams per volume. So by dividing, again, take care of the words. I want to cancel that out, so I know it's got to go in the denominator. So I'm dividing 450 by 1.7 to tell me I've got 264.7 cubic centimeters of magnesium. Likewise, if I have 300 grams of copper, because it's all 750 in a metal block, and I can deduce that 450 grams of magnesium because they tell me it's 60% of the mass magnesium, then all the rest of the mass has to be copper, so 300 grams, and every 9 grams of copper is 1 cubic centimeter. So I can take my 300 grams of copper divided by 9 cubic centimeters and realize I've got 33.3 repeating cubic centimeters of copper. If I add that to the 264.7 cubic centimeters from the magnesium, I realize the total volume, 298 cubic centimeters, and the mass was 750, right? So it's mass per volume, that's what density is. And some students might start the calculation there. Okay, what is the density of the block? That's the mass of the block divided by the volume. They give me the mass of the block. Nice. So it basically cuts your work out for you. If you sort of start with the question and go density, I know an equation for that. Density is mass per volume. And then you look at what you're given. Hey, I'm given the mass. My whole work is finding out the volume. And then you say, well, how will I do that? I kind of started with, oh, I know we need to find the volume. Then we'll plug it back into this. So both are fine ways to think about it, but different students will sort of prefer to kind of have a strategy going into, especially paper 1, where it's like, I know I'm going to be on a time crunch and I want a way that I can just sort of get to the answer as quickly as possible. So the last step here is to take our 750 divided by our 298 and hope that that's one of the answers that's there, and hope even more that it's right. So 2.5 is what I get. And I didn't hear anybody disagreeing with me, so maybe we all think that that's good. A man climbs slowly at a steady speed to the top of a ladder. What is the main energy transfer taking place for the man as he climbs? Chemical to gravitational potential, chemical potential to kinetic, kinetic to gravitational potential, or thermal heat to kinetic? I don't remember about this question. What do you guys think? Anybody have a good sort of discussion on it? Yeah, Krista? If you think it's either B or C, then I think it's C, because I think it's got to be 2 gravitational potential because the word slowly, you know, it's like he's developing potential energy. But I almost want to lean towards like, you know, if this is good chemical potential to kinetic, then why not chemical potential to gravitational? Like he's converting his muscle energy into, you know, gravitational potential energy. But it's like, well, how does he do that? He's got to be moving. It's not like he's not, I mean, he's moving slowly. So it's like his chemical energy in his muscles goes to kinetic energy as he climbs. And as he's climbing, it's becoming gravitational potential. What is the main energy transfer? That's not clear to me. You know, like what's the main one there? I don't know.
Well, I think we could definitely eliminate D.
Can we?
Wait, no.
I think we can, yeah. It's just like, well, it's just such a, you know, kind of an odd question that it's like, well, maybe the answer that's odd is the correct one somehow, because that's the main one. Like there's heat energy, I don't know. So, okay, let's eliminate D and get it to a 30.
So we got a 30%.
I tend to think that kinetic, you know, it's like a man climbs slowly at a steady speed. Why did they put that word in there? Because he's not like he's racing up the ladder with a lot of kinetic energy. I think he's just like slowly turning his chemical potential energy in his muscles into gravitational potential. I'm leaning towards A here, you guys. But I am not certain about that at all, you know, and I would be surprised if it was a different answer. I'm going to pick A and move on in the interest of time. All right, you pick the one that you feel best about. Yeah, I mean, just the word slowly makes me want to take kinetic energy out of there, but because kinetic energy really does have to do with velocity, right? Like the faster you're moving, the more kinetic energy you have. But you still have to be moving somewhat. So, you know, again, we can deal with that one later. During an interval of time, fuel supplies energy X to a car. Some of this energy is converted into kinetic energy as the car accelerates. The rest of the energy, Y, is lost as thermal energy. What is the efficiency of the car? Well, remember that efficiency is the useful energy over the total energy. It looks like the total energy is X. So we're looking for, you know, X in the denominator. And look, that's C. And it does make sense that all of the energy minus what you lose is the useful energy. So C makes sense for a number of reasons. So I'm going to go with that. A railway engine accelerates a train of total mass 800 tons, and they tell us that 1 ton is 1,000 kilos from rest to a speed of 50 meters per second. How much useful work must be done on the train to reach this speed? So I think the best way to think about this is with work kinetic energy theorem. It says that the work done to an object is equal to its change in kinetic energy. How much work must be done to reach this speed? They give us the speed, they give us the mass, or a way to calculate it. So if you know, if it starts at rest, that's kind of nice because the change in kinetic energy is just like how much kinetic energy does it have when it's going this fast. We don't have to like subtract away any initial kinetic energy. It starts at rest. So it's just, do you know that kinetic energy is 1/2 mv squared? And do you know that the change in kinetic energy is equal to work? Because how much useful work is done, you know, to get to that speed. So that's sort of our final answer there. So it just becomes 1/2. The mass is going to be 800 times 1,000 kilograms, right? So 800 tons and each ton is 1,000. And then the velocity is 50 squared. So that's the calculation. 0.5 times 800 times 1,000 times 50 squared. One by 10 to the 9 joules, choice C. So somewhere like that, you know, straightforward, just kind of like, do you know the equations, plug in the numbers, crunch them, solve. Question 18 here reads, a mass is raised vertically. In time t, the increase in gravitational potential energy is E sub p, and the increase in its kinetic energy is E sub k. What is the average power input to the mass? So we can think about like power is energy over time. I don't know if it's as straightforward as just, you know, that. A mass is raised vertically. It's increasing both its potential and its kinetic energy over time t. What is the average power input to the mass? It seems like we're missing something here. Well, you still got that mark scheme handy?
It's D.
It is D, okay. Sometimes, yeah, you can overthink it. You really can. It's like, wait a minute. And sometimes they are just that straightforward. And it's, you know, it's like, again, no question's worth more than the other one. So it's like, well, if you got some kind of a reasonable answer down, you know, might as well just go on to the next one. 19 reads, water flows from a lake into a turbine that is a vertical distance of 90 meters below the lake as shown. The mass flow rate of the water is 2,400 kilograms per minute. The turbine has an efficiency of 75%. What is the output power of the turbine? That sounds like a good one. So output power, let's solve this one using that strategy of start with the question and an equation you know which includes that quantity. So if you read output power, and then this is another clue right here, right? So that's really the equation I think we should use here. So let's say efficiency is useful in over total, useful out over total in. We want to get the output power, so we're solving for the numerator here. We're given the efficiency is 0.75 equals the useful power out, or yeah, power of the total power in. How can we calculate the power in? What kind of energy do you think we got here? Yeah, gravitational potential energy, right? So all the water up here 90 meters above this turbine has potential energy up here that's going to be converted into kinetic energy, and that kinetic energy spins the turbine and so on, generates power. So we have 2,400 kilograms per 60 seconds. M times G times H, but it's power. Okay, remember that efficiency can be both represented in terms of energy or power. And so by giving us a mass flow rate, they're really giving us a way to get to power, right? When we multiply, note how this wasn't mass, that's mass. This is mass per time. So what we really want is the energy, which is this, mass times G times height. Energy per time, the fact that they've given us a flow rate is really what we need to turn the energy into power. So as soon as we divide by 60, then it's power, right? So in other words, even though mgh is the energy, that's just this times this times this. As soon as we go over T, right? So we have M over T, that's how we introduce it. And so this is actually power. Power is the flow rate times G times H. The flow rate gives us mass per time. And so all of this here just gives us the denominator, right? The total power in. We want the useful power out. It's only 75% efficient. Okay, so this gives us like, theoretically, we could generate this much power from that much water. And so we've got 2400 times 9.81 times 90 divided by 60. And that's giving us 3.5316 by 10 to the 4. And so I wrote it like this because I'm multiplying both sides by it, right? Multiply both sides by the power in, that's the power in, and then you get the useful power out. So in other words, we need to take 75% of this to actually get how much power we'll get out of that turbine. So times 0.75, 2.6 by 10 to the 4, which is 26 by 10 to the 3, which is 26 kilowatts, which is choice A. So having a strategy of, if I start with the final sort of answer, the final thing I'm going to solve for and get an equation down for that, then you may tend to make less mistakes when it comes to like dealing with the efficiency. I don't know if maybe this is what it was before we took 75%. So it's possible that you get so wrapped up in the calculation, here, especially if it's not as familiar, like, oh wait, how do I turn flow rate into power? Eventually maybe the units help you figure it out, but then you get this answer and you forget, oh yeah, they told me it was efficiency, what's that again? So by starting sort of with the idea of efficiency, you sort of have a better chance of, avoiding the mistake of neglecting. A wire of diameter D and length L hangs vertically from a fixed point. The wire is extended by hanging a mass M on its end. The Young modulus of the wire is E. The acceleration of free fall is G. Which equation is used to determine the extension of the wire? All right, so let's start with like Young modulus is stress over strain. Stress is force over area. Strain is X over original length. And we really want to make X the subject here. So let's rewrite this. E equals FL over AX. And then we'll rewrite that as X equals FL over AE. So that in terms of force, length, area, and Young modulus, that's what extension is. But I think we still have to kind of see, well, what do we got here? The wire has diameter D, and so we need to convert diameter into area. And that's why all of our answers have like pi's in them. Okay. And then a mass M. And so we can say the force here is going to be the force of gravity. So it's a mass M and it's in gravity field G. So that's where the G comes from. So let's sort of recognize that if I've got a wire and it's got diameter D, what is the area of that? Well, it's going to be 1/2 D, the radius, squared times pi, right? Pi r squared. That's the area of a circle. But we have to put it in terms of, what we were given. So if the area is pi times 1/2 D quantity squared, you have to square everything in there. So the area becomes pi times 1/4 D squared. So this gets substituted in for A, mg gets substituted in for F, and then we see what we got. All right, so the extension is going to be mg, that's the force, right? The weight. The length, they use this kind of lowercase l like that. The area we said is going to be pi times 1/4 times d squared, and then times e. And so this 1/4 in the denominator is kind of clumsy. You can put that 4 back up here, right? Like 1/4 in the denominator is the same thing as 4 in the numerator. So we'll move that back up here. So we're looking for 4 mgl over pi e of pi d squared e. And that's choice D. All right, that's question 20. We're halfway through. Good little alphabet soup there, plus a little pi. 21. The variation of the compression of a spring with the force applied to it is shown in the graph. A block slides along a horizontal frictionless surface towards the spring as shown. The block is brought to rest by the spring. When the spring reaches a compression of 4 centimeters, all of the kinetic energy of the block is transferred to the elastic potential energy of the spring. What is the kinetic energy of the block when it first makes contact with the spring? Okay. So it's brought to rest by it for compression, all of it has been transferred. So we need to calculate the elastic potential energy, and then we can just equate it to the kinetic energy, right? That's all we have to do. How do we calculate the elastic potential energy? It's either equal to 1/2 force times extension or compression, which is sort of the area underneath this curve, right? Or is it? Because they give it sort of like the area underneath it this way. So we can just sort of extract values, from this if we want to. The force that's required to stretch it out or to compress it 4 centimeters is 8 newtons. And so we have 1/2 8 newtons times 0.04 meters. All right, so it's a Newton meter, so we have joules. 0.5 times 8 times 0.04. 6 joules, choice A. All right, so we've made it through Hooke's law, and we're on to waves. All right. Longitudinal wave travels through a long spring. The spring is shown at 1 instant. What is the wavelength of the wave? That's going to be B. All right, so we're going from compression to compression. Not from compression past the compression to the next rare fraction. All right, so, and that's only half a wavelength A. So this is finding the wave there, it's got to be B. Sound wave has a frequency and a speed. What is the shortest distance from a point of maximum pressure to a point of minimum pressure? So this is pretty straightforward. We're going to use the velocity equation to solve for the wavelength. So the wavelength is going to be velocity over frequency. The velocity is 1500. The frequency is 2500. 1500 divided by 2500 is 0.6 meters, right? So reciprocal seconds cancel, we're in meters. And then we half it because the shortest distance from a point of maximum pressure to a point of minimum pressure is half a wavelength, right? Like we just saw in the previous question, like this is maximum pressure. If these are air particles, think about these as like there's maximum pressure where they're all crunched together. So the wavelength is from maximum to maximum pressure to maximum pressure. It's asking, hey, what's the distance from maximum pressure to minimum pressure? It's asking about this half a wavelength. So the path to the solution is to just use the wave equation to calculate the wavelength and then recognize that we only need half of it to get from the point of minimum pressure to the point of maximum pressure to ask for. So choice B. A sound wave is displayed on a cathode ray oscilloscope as shown. They give us the time-based setting. We're asked to solve for the frequency. So once again, with these oscilloscope questions, kind of make short work of it by just saying, I've got 1, 2, 3, 4 divisions per wave, okay? I sometimes like to start with this. Oh, I should say centimeters. 2.5 milliseconds per centimeter. 4 centimeters per wave. Take care of the words, they take care of you. 2.5 times 10 to the negative 3. So remember that millisecond, milli means 10 to the negative 3. 2.5 by 10 to the negative 3 times 4 centimeters per wave gives me 0.01 seconds per wave, right? Seconds per wave, that's the time period. And if I need to know the frequency, it's just 1 over that. So I take the inverse. 1 over 0.01 is 100 hertz per speed. Moving right along here, it says a car traveling in a straight line at a speed of 30 meters per second passes near a stationary observer while sounding its horn. The true frequency of the sound from the horn is 400 hertz. The speed of sound in air is 336 meters per second. What is the change in the frequency of the sound heard by the observer as the car passes? I think this is a I don't know. I guess we have to calculate a number of things here. I think what we need to do for this one is calculate the observed frequency based on the frequency of the source using the Doppler effect. And I think we need to calculate both as it speeds away and as it speeds towards the observer, and then take the difference in these frequencies. Because it's saying, what's the change in frequency heard by the observer? So it's like he's going to hear some high-pitched frequency higher than 400. He's going to hear some lower-pitched frequency lower than 400. And the question is saying, what's the change in the frequency? So it's going to be 400 something minus 300 something. Okay, is our final answer. Remember, we add in the denominator to deal with receding motion, and we subtract in the denominator to deal with approaching motion for Doppler effect. All right, so computationally it becomes 400 times 336 over 336 plus 30. This one's going to be 400 times 336 over 336 minus 30. 400 times 336 divided by 366. So as the car speeds away, that frequency is 367.2. As the car speeds towards, 400 times 336 over 306 is going to be 439.2. 439.2 minus 367.2 is 72 hertz. Let's see. Students that calculate this value and then say, oh, the change is going to be the difference between that and that. We'll calculate this answer. Students that calculate this one, oh wait, no, because that's 367, so I guess that would be that. In any case, you can see how, there's always some reasonable answers there that are incorrect. Which list shows electromagnetic waves in order of increasing frequency? Well, I'm going to look for gamma rays at the end there, and then ultraviolet. Yeah, so D looks good. All right, gamma rays have the highest frequency, so if you look for the ones with those, and then you start saying, well, radio waves, that's the lowest. We'll go from like the highest to the lowest, and where are these? They'd have to be in between somewhere. So radio is the lowest frequency, gamma ray is the highest. And then those fall in between. Good. Another wave question. Looks like we got our MELDS apparatus here. It says the diagram shows a steel wire clamped at one end. The other end is attached to a weight hanging over a pulley. A vibrator is attached to the wire near the clamped end. A stationary wave with one loop is produced. The frequency of the vibrator is F. Which frequency should be used to produce a stationary wave with two loops? Well, that wave would have to occur, what, twice as frequently? Right? In other words, we want a wave that looks like that. And do you see how that wave occurs twice as frequently? Like in other words, there's the wave that was before, and now it's twice, you know. So I think it's C, right? So double the frequency. Maybe there's something wrong with that. Maybe I'm just simplifying it too much. But let's move on here. A parallel beam of light of wavelength 600 nanometers is incident normally on a diffraction grating. The grating has 300 lines per millimeter. What is the total number of intensity maxima for the grating? I think I told you all that this is a very typical question, okay, that we'll run into here. Diffraction grating, does anybody remember the equation for that? Sort of stuck if you don't, all right? So you just become like, oh, I forgot, and you go on to 29, and you hope there's not another diffraction grating. So the equation, you design an equation for a fraction grating, okay? You design an equation, d sine theta and n lambda equation. D sine theta and lambda. We really have to solve for n and then double it and then add 1. Remember that, how you sort of say, I can't have a quantity sine, you know, greater than 90, okay? So like, this quantity is maximized at 1. So we can really just kind of take the sine theta out of it. Or if you want to, you can say, well, I know that anytime I get a question like this, I sort of make the angle theta 90 degrees. Remember the sort of way that this is set up is the angle relative to the 0 order. So you can't get an angle more than 90 degrees, okay, relative to the 0 order. Like here's the light, you know, passes through the grating, and then the 0 order is right here. And there's the first, second, third. We're going to calculate n with maximum sine theta, 90 degrees or sine theta equals 1. They don't give us d, but they give us a way to calculate it. Like, sure. Fine. Harrison to check out. So we're making sine theta 1, or you're making theta 90, which means, you know, sine 90 is going to be 1. Remember, d is the actual distance between each line. So if they tell us there's 300 lines per millimeter, call this n. N equals 300, you know, lines per millimeter. What we want to know is how many millimeters per line, or even better, how many lines, how many meters per line. So d is 1 over n. All right, when you're given sort of data like this, if you're given the number n of lines per millimeter, you need to know the distance between each one. So it's going to be 1 over 300. Hold on, let me do it like this. There's 300 lines per 1 millimeter. So that means that there is 300,000 lines per meter, which means there are 0.3 by 10 to the negative 6 meters per line. That's what D is. Okay. 3.3 by 10 to the negative 6 meters per line. We want it to be in meters because the wavelength, we're going to convert that into meters also. All right, 600 meters. So solving for n now, we'll divide each side by the wavelength, lambda, and now I'll write it as d 3.3 by 10 to the negative 6 times the sine theta, which, you know, if you want to, write sine 90. That's going to be 1, it won't change the computation, divided by 600, and then nano is 10 to the negative 9. And remember, this is meters, this is meters. This, remember, just solves for the number of maxima on one side of the zero order. To answer this question, you still need to double it to get the number on the other side of the zero order, and then add 1 to get the zero order itself. That will be the number of maxima seen. So we got 3.33. So I get 5.55 for n. So you first round that down because you can't observe a fraction of an order. You say, well, I would only observe 5 orders on one side of it, which means I'd observe another 5 on the other side, which means the answer to this question is 11 because you added the zero order. Remember, this angle theta is the angle, if n is 1, the angle to that first order. If this angle theta here, theta 2, that's to the second order. Well, what we've solved for is just saying, well, how many orders do we get? Let's just maximize theta, like all the way down here, 90 degrees, right? Plug in 90 for that, then it's 1. So we got 1, 2, 3, 4, 5. We would have got all the way up to 5 orders. But we still get 1, 2, 3, 4, 5 up there. 5 plus another 5. Don't forget about the zero order. That's why you get 11. The variations on this theme, okay, almost like every single paper has a question like this. You know, I think we did one with like an eyeball that was floating, you know, and like how many, you know, fringes would the eyeball observe? So it's the same kind of question. You just have to remember to double n, you know, then add 1 for the zero order. And then, you know, the other conversions that we always kind of have to deal with. This is kind of a good question like this because it folds in sort of every complexity you can encounter. They won't always give you D. They'll give you a way to calculate it. They won't always give you a way to calculate it like friendly. You got to convert millimeters to meters. And you got to remember, you know, what to do with the angle here. And you got to remember the equation. If you don't have the equation, you kind of just stuck right there. You just take a guess and then move on. But choose maybe an odd number. Oh, they're all odd, so that one won't be there. But it's always going to be odd, right? Because you're adding 1, you know, at the end to it. A pattern of interference fringes is produced using a red laser, a double slit in the screen. The screen is 3.5 meters from the double slit. The light from the laser has a wavelength of 640 nanometers. The pattern of the fringes is shown. And what is the separation of the slits? So this is two-slit interference. It's lambda equals AX over D. They're asking us to solve for A. So A is going to be D lambda over X. D is the distance to the screen, and so that's given 3.5. The wavelength is given 640 times 10 to the negative 9, right, nanometers. So 3.5 is D, the distance to the screen, that's what we call D. Wavelength, lambda, don't forget to convert nano. Now, X is the distance between two of these, right? These are all the bright fringes. And so we could say, well, there's 72 millimeters per 1, 2, 3, 4 fringes. Right. 18 plus 18 plus 18 plus 18, that's 72, right? So you just have to kind of take, well, they've measured between 5 of them, right? So there's 18 centimeters between each one, right? There's like the distance, there's 1, 2, 3, 4 spaces, right, between these 5 bright fringes. So yeah, don't divide by 5, right? You got to divide by 4. And then to really prove it to yourself, say, well, this gives me 18. That's saying that's 18, that's 18, that's 18, that's 18, right? Adds up to 72. So this is going to be 18 millimeters. All right, let's crunch the numbers. 3.5 times 640 by 10 to the negative 9 divided by 18 by 10 to the negative 3. And we've got 1.2 by 10 to the negative 4. There's A. 1.2 by 10 to the negative 4, I guess. The diagram shows 2-point charges P and Q, which lie 90 degrees apart from the circle radius R. Positive point charge at the center of the circle creates an electric field of magnitude E at both P and Q, which expression gives the work done in moving a unit positive charge from P to Q. I just think it's 0. It has something to do with like this, you know, like no work is done because, you know, it's moving around a circle. Okay. Let's move on and maybe come back. My intuition tells me it's 0 there. Something about moving around a circle, you know, the cosine of the force that's being exerted. Yeah, let me come back. The diagram shows 2 parallel horizontal metal plates. The top plate is positively charged, and the bottom plate is earthed. A small charged liquid drop midway between the plates is held in equilibrium by a combination of its weight and the electric force acting on it. That's good old Millikan's oil drop experiment, right? Acceleration of free fall is G, electric field strength is E. What is the polarity of the charge on the drop and the ratio of the charge to mass on the drop? Well, if this is the positive plate and this plate is Earth, we can think about the electric field and how would a positive charge move would be repelled. So this must be a negative charge, okay, for it to be held there, right? So the force, the electric force is going this way on it. Its weight acts straight down, right? Here's the Earth right here, so the weight's going that way. Electric field E. Electric field E is force per charge, or the voltage per distance. The force, because it's held in equilibrium, okay, so we know that the weight mg is equal to the electric force. Like the electric force is also mg, right? Because it's held stationary. So like whatever the mass is, it's equal, you know, to the times the gravity field strength is equal to the electric force over acting up. So the electric field E is equal to the force, well, the force on it is equal to its weight mg. So we need to somehow put this, the charge to mass, in terms of the electric field here, right? That's the charge. So we just kind of need to rewrite this. See how I have it? I have like mass to charge with the G over here, like divided side by G. Now I've got mass to charge, but they want charge to mass. So we do the old algebra flipperoo. There you go. Kind of, you gotta trust the numbers. So electric field strength is force per charge. All right, electric field is the force, but the force is mg. All right, it's the force that we just said is the weight per charge q. M per q, that's mass per charge, but I want charge per mass. Okay, so it's like, well, if I've got mg over q, well, first of all, get rid of that g, right? Divided side by g, so I have E over g is m over q. But I don't want m over q. They asked me for q over m, so that's when you just do the old algebra flipperoo. All right, m over q is E over g, and q over m is g over e. So this Polarity is negative, and Q to M is G of T. Okay. The diagram shows the symbol for a wire carrying a current I. What does this current represent? The charge flowing past the point in the wire per unit time, the number of electrons flowing past the point, the number of positive ions, the number of protons. Well, we just have to keep it very general. It usually is electrons, but it's just charge. It could be protons or positive ions or whatever, but some charge. And charge per time, that's what current is. I equals Q over T, Q is charge, and it's usually electrons, but not always. Which values of current and resistance will produce a rate of energy transfer of 16 joules per second? All right, so we say what equation relates current, resistance, and this is power, right? Rate of energy transfer is power. So just because the word energy is there, you say, oh, it's a joule per second. A joule per second is a watt. You know, then say, hey, which values of current and resistance will produce a power of 16 watts? That's a little bit friendlier of a question, because then it's like very clear, oh, that's a power. But you should know energy transfer, the rate at which energy is transferred, the rate at which energy is converted, that's power. And so we're just looking for an I squared R, right? I squared R that equals 16. 1 squared is 1 times 4 is 4. 2 squared is 4 times 8 is 32. 4 squared is 16 times 1 is 8. Right. It's helpful if you have all of your equations in mind and you don't have to like derive a different one. So if you remember like, oh, power is I times V, and I have to make law or something like that, but just like knowing the equation, like I was given this and I know that equation, you know, solves for power. Which component has the IV graph shown? The metallic conductor and the resistor of fixed resistance are kind of like the same thing, and they obey Ohm's law, so they're kind of like this part of it. It's like any kind of like there, you know. So that's B and C. It's a straight line, obeys Ohm's law. Ohmic components, right? Semiconductor diode, that's the whole idea of the threshold voltage. Eventually it reaches that threshold voltage and it starts to conduct before it's like infinite resistance. And this guy is the filament lamp. So it starts to trail off. So increases in voltage don't give us the same increase in current they once did. So that's a filament lamp, not a non-ohmic component. The circuit shown includes a cell of constant internal resistance and an external resistor R. A student records the ammeter and voltmeter readings. She then connects a second identical external resistor in parallel with the first external resistor. What happens to the ammeter reading and to the voltmeter reading? I think D. What do you guys think? D for this one. It's like we got this set up, and then we put another resistor in parallel with this one. What happens to this ammeter and this voltmeter? Oh, wait a minute. Why would the ammeter increase? If we put more resistors in parallel, you open up more paths for electrons to flow through. So the overall circuit resistance decreases. So if there's less resistance in the circuit, then it's going to draw more current from the battery. And this is like the total current, right? That's going back into the battery. So I think if we add more resistors in parallel, then it gives more paths for the electrons to flow through. Okay, and we're going to decrease the circuit resistance. If you have a simple circuit like, you know, that, and just give yourself the friendliest numbers, like let's just say 12 volt battery, that's a 3 ohm resistor. Okay, so what's the current? 12 divided by 3/4, right? But if I put another one like this, 3 ohms, Well, now remember what I've done to the circuit resistance. Just because there's more resistors in the circuit doesn't mean that there's more resistance, okay, because of the way that I've wired them. So now the electrons don't just have to go like this through this loop. Now they can go through this loop too. So what's the resistance in this circuit now? It's just kind of like if we force students to go this way to the lunch line, but it's like, hey, there's open up those blue gates and you can go that way too, right? There's less resistance everywhere in the school or on campus. There's less resistance everywhere. And you can prove it with like, you know, a calculation like this. 1/3 plus 1/3 is 2/3. So 1 over R, so R would be 1.5, right? 3/2. So by adding another resistor with the same resistance in parallel to it, remember the resistance first was just 3. There's one resistor and it's 3. Well, you add another 3 ohm resistor, but now the circuit resistance is 1.5 because we're summing reciprocals, right? We're always going to have less circuit resistance. And now here I didn't really think about this. I don't think it changes the answer. Maybe it does. So as we draw more current, we're also going to lose more volts. So maybe this would have to decrease also. Yeah, my bad, you guys. Come on, internal resistance. I think it's C now. Because it's true that if we add another resistor in parallel, this number should go up. But as it does, remember what this means when you have like a dashed line around this guy here, they do tell us there's an internal resistor. Then you say, oh, there's another relevant equation I need to keep in mind. As I drive more current I through the battery, that's constant, right? R is like however good they built this battery has a certain amount of internal resistance. But if I drive more current through it, I'm losing more volts, right? Those are the lost volts. So now there's going to be less terminal PD, right? The EMF is a 9-volt battery, but now I'm losing more volts because I'm driving more current through it. So now I don't have all, you know, as many volts as before. So my original thinking was, oh, it's in parallel, voltage across parallel branches, what stays the same? Because I was only thinking of that chapter 9 idea. I need to get to chapter 12, practical circuits, internal resistance, right? So I should decrease the voltmeter while I increase the ammeter. I changed my mind. I don't want to go with D, I'll go C. That's sometimes what it takes, right? You just kind of talk it out, think through it a little bit, and then you improve your understanding. That's why we're here, to learn. All right, I feel pretty good about that. Moving right along. Oh no. Got a full pager. This is like a good one for you guys. I could probably go to the cafeteria and see how they're doing down there. All right, it says a computer is used to detect the change of position of a switch. To detect the change of position, the computer requires a potential difference of 0 volts to its input at one switch position and a potential difference of between 5 volts and 7 volts at the other switch position. For each of the circuits, assume the battery has negligible internal resistance. Which circuit provides an input voltage to the computer that enables it to detect the change of position of the switch? And this is what I mean when I say paper 1 will like, yeah, we did potential divider circuits, but like, you really got to think through that, you know, like that's kind of unfamiliar. There's always, you know, a couple like this here, and maybe it's not that bad once we kind of sort of look at it more clearly. Which circuit provides input voltage to the computer that enables it to detect the change of position in the switch? All right, let's look at each of the circuits here and then try to make sense of the question. We have potential divider circuits, and here it's like they put a switch here, and we have equal resistors, and they put the divider here. So it's like, this was just gonna take this 9 volts and half it, so it'd be 4.5, right? Because each of these is the same amount. So it's like 4.5 volts dropping across this, 4.5 volts dropping across this. This is a potential divider. We're dividing this potential difference. So that's 9 volts. We drop 4.5 volts across this. So now there's only 4.5 volts available across this. And so that's why we could hook this up. Well, 4.5 is not between 5 and 7. I really think whatever we get here has to be between 5 and 7. They're telling us that we need the position at one switch position of PD of between 5 and 7 at the other switch position. So the fact that we get 4.5 volts here is less than 5, and I think we can eliminate choice A. So I think that's the way we sort of need to approach these circuits here. And then for these other ones, it's like, well, the switch is here or the switch is here. You know, so it's kind of like, let's look at this one. All right, so we do 9 times 2 divided by 3. So this is the equation for potential divider circuits, right? Where it's like the voltage out is equal to the resistor 2, this one, over the sum of the resistors times the voltage in. So when we apply that equation, we get 6 volts right here, which is right in between 5 and 7. And so that's enough for me to choose B and move on. If I were to close this switch, okay. But then before we just have 5. Maybe the problem with these circuits is you could never get, like if you break this, then you get 0, right? Like it shuts off the whole circuit. There's no loop. But here, I think even with this open, there still is a path for the electrons to flow through. So I don't think you could ever get the 0 volts out of these. But I don't really know. If we need to read that much into this problem, we can just say, hey, if we get a number here that's between 5 and 7, we're good. Yeah, fine.
Even if you did solve C and D, C you get 1.8 volts, get 7.2 volts.
So they would still fall out of the range, further sort of proving their incorrectitude. Is a word at this point. All right. Another circuit one. Why not? In the circuit shown, the battery and ammeter have negligible resistance. The following combinations of resistors are each separately placed between terminals X and Y of the circuit, which combination will give the ammeter reading of 8. Okay. This is going to be fun. So here we've got 1/2 plus 1/3 equals 1/R. In my calculator, I can go 1/2 plus 1/3 inverse. So this R here, this combination of resistors is 1.2 ohms in series with this, and so this choice A here has a circuit resistance of 2.2 ohms. If I equals V over R, and V is 12, and R is 2.2, then the ammeter would read this, 5, not 8. So 8 can't be right. Do the same thing here. 1 over 1 plus 1 over 3 equals 1 over r. 1 over 3 plus 1 inverse. So this part here has 0.75. So I'm using the reciprocal equation to collapse the parallel branch into this some value, 0.75, right? So like that's the reciprocal of the sum of these reciprocals, 0.75. In series then with 2, so it's 2 plus this is 0.75. And note how 0.75 is less than 1 and it's less than 3. And note how the 1.2 that we got for this was less than 2 and is less than 3. So that further shows that like you'll always get a circuit resistance that's less than any individual resistor when you add resistors in parallel, right? Because and again, this sort of you can picture it as you're opening up more paths for the electrons to flow through. So there's going to be less resistance for them. I should say electrons, charges, right? Usually electrons. So if we did the same thing, we're plugging in just whatever we get for the equivalent resistance of the circuit in here, 12 divided by that until we get 8. So that's no good. Now here we've got what? We've got a 3 ohm in series with these 3 ohms here, this 1 and this 2 ohm resistor are in series with each other. So there's 3 ohms of combined resistance on this path, but in parallel with this one. And so this one would be 1/3 plus 1/3 equals 1 over the circuit resistance. That's 2 over 3 equals 1 over the circuit resistance. And so the circuit resistance is 3 over 2, or 1.5 ohms. And 12 divided by 1.5 is 8. So that's your answer right there, towards C. For completion's sake, 1 divided by 2 plus 1 plus 1 divided by 3 inverse. This one have a pretty low circuit resistance because everything's in parallel. So 12 divided by 0.54 gives you 22 amps. Red for that one. At that point, you might say, well, if I can get 22 amps, I'll go all the way back to question 1. Change my answer, if I thought that it might have been A. So 22 amps, yeah, I've got 12 for a fan. All right. The last thing that we studied in December, this stuff, question 38. The table lists the nucleon number and the proton number of various nuclei. The nuclei are represented by the letters L to T. Which row in the following table correctly shows 3 nuclei of the same element and 3 nuclei that have the same number of neutrons? I feel like we did this one before also. I don't know if we did it in this class, maybe another class. So which row on the following table shows 3 nuclei of the same element? Okay, the same element, could it be L, M, and N? We know that the same element are going to have the same number of protons, right? That's what defines them. So could this be, could L, M, and N be the same element? Yes. Same numbers of neutrons. And so to get neutron number, we just need to subtract this from here, right? Like this is all the nucleons. And so I'm just going to create a third column, neutron number. I'm just going to calculate all those real quick, and I think it'll make it a little bit easier to solve. 227 minus 89 is 138. So 226 minus 89 has got to be what? 137. Right? All right, check my calculator. 137. So this one's going to be 136. 227 minus 90. That's 137. So 226 minus 90 is 136. 225 minus 90 is 135. 227 minus 91 is 136, 135, 134. All right, so now I got neutron numbers there. Okay. Do R, P, and N have the same number of neutrons? So you got R, 136, P, 136, and yep, there you go. What's that? Done. You want to disprove all the rest of them? No. Yeah, MPS. M is 89, P is 90, so right away they're not the same element. They got different numbers of, protons. OPQ? Well, OPQ are all the same element, but then that must mean that MPS are not the same number of neutrons. So let's check that out. M was 137, P was 136. So there you disprove this one. RPN, R was 91, P was 90, N was 89. So again, so this one doesn't pass that one. This one doesn't pass there. Only A is correct. That should be good for one day for paper one. Does that bother anybody if we get to the last page? It's like, oh, we just have 2 more left. You gotta finish it. It would bother me. It really would. Like, oh, we got it. Like, that is probably enough for one day. It's enough for several days. But this is what you got to do. Think about sitting down for one of these and doing it in 75 minutes. It would take them a lot longer than that. I know we've stopped this kind of discussing things like that, but you're just sitting down, crunching away, and sort of. It's a tough test for sure. You've got until June 9th, 2021 to prepare for it. Tomorrow will be January 9th. So January, February, March. 5 months from tomorrow, you'll be faced with this kind of a time.
Is that during the summer?
Yeah. So school ends, I think, on the week before. It's not too bad. I mean, usually that's around the time they always administer them, but we usually end school like weeks before. So this year it's a little bit different because we end school a bit later because we started it. A radioactive nucleus is formed by beta minus decay. The nucleus then decays by alpha emission, which graph of nucleon number N plotted against proton number Z shows the beta minus decay followed by an alpha emission. So beta minus decay, we're ejecting a negatively charged particle from the nucleus because a neutron has become a proton. Okay, so I think about it like, how do you get a negative charge out of the nucleus? Because you had something that was like a neutron that was neutral because it had positive and negatives in it. One way to think about it, not really correct, but it's okay. So this negative is ejected, that's our beta particle, the positive remains behind. So the beta emission, okay, is gonna jump us up on proton number. Remember, Z, this is a proton number. So we need something that goes like this, from 91 to 92. And that's the only one that doesn't. So B, right, this one goes from 91 to 90. So there's our beta emission, right? We go up on the periodic table. We transmute from this chemical 91 to 92, but then the alpha emission brings us back down to brings us down 4 nucleon numbers from 234 to 230, and it brings us down 2 proton numbers. Remember that the alpha emission is a helium nucleus. And so anytime you emit an alpha particle, that's one of these, right? It jumps down 2 this way because there's 2 of those charges are positive, but it goes down 4 a nucleon number because 2 of them were neutrons. So this sort of line here is alpha decay. So there's beta decay, alpha decay. Choice B is correct there. The last one says, what are the structures of the proton and of the neutron in terms of quarks? And so a proton is 2 ups and a down, and a neutron is 2 downs and 1 up. So that's choice C, and that's pretty nice because it's just either know it or you don't. All right.
Presumably they'll vote.
Sometime around, I'm not sure. Yeah, 11:45. So that was May, June 17, April 11. All right, here we go. One, D, 2D, 3A, 4D, 5C, 6 was B, 7 B, 8 was C, good, 9 was D, 10 A, 11 A, 12 was D, good, 13 C, 14 A, 15 A, 16 C, 17 C, 18 was D, 19 A, 20 D, 21 was A, 22 was B, 23 was B, 24 B, 25 C, 26 B, 27 C, 28 C, 29 was A, 30 was A. All right, that served me well. We'll come back and explain this in a little more detail about, why is this zero? And it really does have to do with any kind of circular motion, like something moving in a circle. If you think about like the force that's causing it to do that, it's a center seeking force, and then the direction of its displacement is what? Perpendicular to that. And so cosine 90 is 0. So that's why, it really has to do with this, the sort of from P to Q. So it's like it's moving this way, the force is this way. And so the angle between those vectors is 90 degrees. And so no work is done, okay, because the cosine of 90 is 0. 31 is B. 32 is A. 33 C. 34 A. 35 C. Good thing we caught our mistake there. 36 B. Good. 37 was C. Good. 38 was A. 39 B. 40 C. Nice. 40 out of 40. All right. And that's what you guys need to do on V1. Just get them all correct, okay? because that's really tough to do, especially on paper one. You know, those are some tricky questions before. See how they can kind of stump you, you know, but I think, you know, the more that you kind of go through, one, the more likely you are to see like a familiar question, like, oh, I've seen one like this before, I know, you know, and that's really what I kind of relied on. Like, I've been, you know, studying physics for a number of years now, and I just kind of remember this, you know, like, oh yeah, circular motion, there really is no work done, you know, because it has to, you know, sort of do with how the vectors are sort of positioned relative to each other, the angle between 90 degrees. And so you don't really need to, you know, sort of wrap your brain over what kind of, you know, ratio of the circumference, which is kind of what maybe you might get caught up thinking if you're thinking of any of these answers. It's really more of a conceptual question, which is like, oh, cosine 90 is 0, no work is done. That's why it is correct. All right. That's paper one. Now let's go through a paper two. This one is October, November, 2016, paper 22, for anybody that wants to follow along. And now we'll compare and contrast. We'll see like, which one is the worst paper? Paper one or paper two here? I don't think we'll have time for paper three today. That wasn't my goal though. Define pressure. Anybody define pressure as you sit for paper two? 46% of your grade, you know, relies on your demonstration of your mastery of the learning objectives. At this paper, would anybody be able to define pressure as they sort of staff for that? What I'm feeling right now. Would they give you a mark for that? Maybe a smiley face, but they'd still take the mark away. You want to have a good physics definition. Pressure, force per area. All right, and don't just write that, you know, write it out. You know, pressure is the force per area. The force acting per unit area. You know, so I'll just give you sort of the essence of it. Show that the SI base units of pressure are this. Be my pleasure. Pressure is force per area, and force is measured in newtons, and area is measured in meters squared, and a newton is a kilogram meter per second squared. And we still have the meter squared down here, and so that equals kilogram per meter per second squared. So far, so good. Gas flows through the narrow end, the nozzle of a pipe. Under certain conditions, the mass m of gas that flows through the nozzle in a short time t is given by this. So mass over time, right? That's the flow rate is equal to this guy over here, where k is a constant with no units, c is a quantity that depends on the nozzle size. Rho is the density of the gas arriving at the nozzle, and then p is the pressure of the gas arriving at the nozzle. Determine the base units of c. So we'll start with what we know on the left side. If it's mass over time, then it's kilograms per second. And that's going to be equal to K. We don't care about it because no units. All we care about is the units for this one. C is our mystery thing that we're going to find out. So I'll just leave it as C for now. And then underneath the radical here, so I'm just going to go squared, squared, squared. All right. Let's just square everything, and then we sort of remove the radical. In other words, at this step here, you could have said, I'd rather deal with an equation that looks like this than that. Okay, like get those things out of the radical. It's like, well, I'd rather have a radical than all these exponents. No, you wouldn't. You know, deal with the exponents, not the radical. If you have a way to work underneath the radical, you know, go for it. All right, and so now we got C squared there. And now we've got the units of density. So that's going to be kilograms per meter cubed. And then we've got pressure, which we just did up here. Remember, that's pressure. So we'll just plug that all in. Kilogram per meter per second squared. All right. So it looks like we've got now our kilograms squared. Good, because we wanted that. But on the denominator, we've got, let's rewrite it. Kilograms squared per second squared equals c squared. And we've got kilograms squared over meters to the 4th second squared. So everything is good here. Kilograms squared per second squared. But what must be the units of c such that when we square it, we'll cancel out these meters to the 4th? We got to have meters squared, right? If c is, so it must be like an area quantity that depends on the nozzle size. Hey, that makes sense. It's the area, right? They're not saying c is the area, because then you'd be done. You just know area is this. It's some quantity that depends on the nozzle size. Wouldn't area depend on that, the size of the nozzle? So by plugging in meters squared for c, then you'd say, okay, meters squared, a meters to the 4th, that cancels out those. Kilograms squared per second squared is kilograms squared per second squared. So that's kind of what I've marked for that. A ball of mass 0.03 kilograms moves along a curved track as shown. The speed of the ball is 1.3 meters per second when it's at point A and a height of 0.31 meters. The ball moves down the track and collides with the vertical wall at point B. The ball then rebounds back up the track. Because we assume that frictional forces are negligible. Calculate the change in gravitational potential energy of the ball in moving from point A to point B. The change in gravitational potential energy will just be based on sort of this change in height that it goes to 0. So we have 0.03 kilograms times 9.81 meters per kilogram times 0.31 meters. We'll get Newton meters, which are joules. 0.03 times 9.81 times 0.31 is 0.091233, and I would report my answer as 0.09. Show that the ball hits the wall at B with a speed of 2.8 meters per second. I think what I'll do is just say that the velocity is going to be equal to root 2gh. So, well, how do you know that? I'm taking the potential energy that it possesses. Oh, wait. This will be the velocity it gains as a result of the change in height. I'll still have to add the 1.3 meters per second it started with. Look, it doesn't start at 0. It starts at a non-zero speed. So this equation here comes from equating potential energy with kinetic energy. The frictional forces can be neglected, like they tell us, then all the potential energy will show up as kinetic energy. And so you can just take mgh and equate it to 1/2 mv squared. It won't matter how massive something is in terms of how fast it's going to be going. Okay. All that matters is the gravity field and the height. And so if you just reorganize this for velocity, you get this, right? Multiply both sides by 2 and take the square root. So this is a nice little equation that relates how fast something will be traveling if it falls a given height, in the gravity field. So if we do that here, we can deduce that 2 times 9.81 times 0.31 square root of that. This gives us 2.46. It was already going 1.3, so that doesn't work. Yeah. 2 times 9.81 times 0.31. Take the square root of that. Yeah, I get 2.46 for that. What are we missing? Speed of the ball is 1.3, one is at point A. The ball is down, blah, blah, blah. So on.
What paper is this?
This is paper 22 from October, November 2016. And I'm stumped because I don't see any mistake in this. They tell us the speed should be 2.8. We get 2.4. Nothing wrong with that. It's just that we should be able to add in the initial speed, right? Like it's already going 1.3 while it's still at that height. So if it converts all the potential energy from here to here, it should be gaining another 2.4. So it makes me want to say the answer is 3.8, not 2.8. So what am I missing? Yeah, I mean, look, it starts out at a speed of 1.3. I mean, I double checked it again and again. So the velocity, that's something would gain by, traversing 0.31 meters in Earth's gravity field should be this. It tells us it's initially going 1.3, right? So it's just like, okay, it was already going that fast, and now it's going to go this much faster. That's 3.8, not 2.8. I thought about that, but there's no friction, so it's like that still is the height. You know what I mean? Like it still is gonna convert all that potential energy to kinetic energy, and then nothing's gonna slow it down at all. Show that the ball hits the wall at B with a speed up. Well, I can't do that. I mean, we don't need to this way, but you're right, like, well, maybe we did, and that's why it's all messed up. So I said, well, let's go back to here. Like we said, it's gonna change its gravitational potential energy, 0.09 joules. So if we just kind of said, well, that was the mgh, right? Like there was the mass. That's how we got this. So we could have said, well, we figured this out. Like we don't need to just solve it. We could say the potential energy that it changed was 0.09 joules, and that's equal to the 1/2 mv squared. But see, it's the same thing. It's like, well, because that mass was in here, I'm just dividing again by it. And that's why it's sort of, like the mass is going to cancel out anyway. But even if you set it up like this and plugged in 0.3 and, solved it for V, you'll still get this value. It basically agrees with this mathematically. So we can show that we're gaining 2.46 meters per second on velocity. We start out with 1.3, and I just can't see how that's 2.8. Anybody have any thoughts on this one? Anybody see something that way? Gotta read through it again very carefully. I don't know what we're missing. You're looking at the mark scheme? Oh, that's what I want to do now. What are they saying?
I mean, it is the same thing with theory.
Do they get 2.8? Yeah, I was gonna say, like, there's never a mistake, you guys. Like 2016, it would have found it by now. So it's like it was published. Hey, we messed up. What's going on here? 22. We got 40 out of 40 on paper one. On almost all paper one's the tough one. Here we are looking at the marks in my question 2. That's how it goes sometimes. All right, October, November, 16, 22. What in the world's going on? All right. So show that the ball hits the wall with a speed of, they have the initial, so looking at the mark scheme, let me actually let you all take a look at this with me here. All right, so this is their mark scheme, and they do somehow get to 2.8. All right, so let's see how they got there. It says the initial energy is 1/2 mv squared. Okay, so they give us they calculate the kinetic energy initially. 0.5 1/2 mv squared equals, that's solving for the velocity, it equals the kinetic energy plus the potential energy. Or 1/2 mv squared equals, this was the initial energy plus this. So, okay, here was the mistake in our thinking. I got it. The speed of the ball is 1.3 meters per second when it is at point A. So it's kind of like it hits the track with this much speed and therefore has as much kinetic energy as that much speed would give to an object with such a mass. But it's not necessarily true that that speed just gets added to the sort of speed here. Okay, we can't just sum the velocities like that. So the way that they're approaching the calculation is to say, turn this velocity, this speed here, into kinetic energy. All right, figure out how much kinetic energy did the thing have initially. We know how much potential energy it gained. And so we can then take these energies and set it equal to 1/2 mv squared and solve for v. And then we'll solve, then we'll get the correct speed. Okay. So that's one of the paths that they suggest. I think there's another way to do it. And we could have solved it also. So here we would take 1/2 the mass times this 1.3 squared, and that would give us, a certain amount of energy, 0.5 times 0.03 times 1.3 squared. 0.02535 joules plus the 0.09 joules that we gain from the potential energy, so the plus 0.09, and that gives us 0.11535 joules. well, so that's the total energy, right? Like it had this much kinetic energy, and then it gets this much, more potential energy converted, and so that's the total kinetic energy now. So we set that equal to 1/2 mv squared and solve for v. So take that divided by 0.5, divided by 0.3, the mass, and then take the square root of, so v squared is 7.69. 2.77, which is indeed about 2.8. Why can't we just add that blank?
Because when you have a problem like this and you're adding two terms together, you can't take the square root of each term individually unless you're multiplying them. So you would have to take the square root of the whole thing. Like you'd have to do the 1.3 squared plus, and then the 2 times gravity.
This one down here.
Yeah, you would have had to divide you would have had to with 1.3 meters per second. You would have to square that and put that under the bracket with the rest of it.
Plus, so like this.
Yes, except you have to square 1.3.
So there is maybe a path to the solution along these lines, but maybe not the most sort of straightforward way. I'm trying to avoid it. Yeah, so it's like, well, this thing has 1.3 meters per second. You say like, and then we're definitely converting 0.9 joules into kinetic energy. So if something started at rest here, okay, let's think about this. We just put a ball at rest and we let it roll down, no friction. It's going to get this much velocity, 2 point whatever we saw, 2.46. If we then throw a ball at 1.3 meters per second, down, and we let it do the same thing, okay, because it's already going a certain speed, how does that affect it? I really think that it's like an interpretation of the question of like, it has speed, it has kinetic energy here, but we can't really rely on the fact that it keeps that speed as it enters the ramp or something like that. Like it has that energy, but why doesn't it work to where we could just add this speed back? Yeah, you were saying mathematically, we could add the square root. Anyway, we'll save that for another day when we haven't been doing physics. It says the change in momentum of the ball due to the collision with the wall is this, and the ball is in contact with the wall for a time of 20 milliseconds, determined for the ball colliding with the wall, the speed immediately after the collision. So the ball struck the wall with velocity 2.8 meters per second, and the mass of the ball was 0.03 kilograms. Then the momentum of the ball was 0.0831. I rounded I used the actual value in my calculator. Let me use the rounded value. 2.8 times 0.03. 0.084 will make it. Kilogram meters per second. The change in momentum of the ball due to the collision is this. The ball is in contact with the wall for a time of this. Determine the speed immediately after the collision. So the change in momentum is the final momentum minus the initial momentum. And the change in momentum is 0.096. The final momentum minus the 0.084. Then I could solve for the final momentum. Oh, wait, hold on a second now. The change in momentum is this. The final momentum, if it's positive, I'm subtracting away negative, okay, because these vectors oppose each other. That's important to remember too. So this is minus negative or plus positive, so I subtract this. So 0.096 minus 0.084. 0.012 equals the final momentum, and final momentum is mv. So I can divide each side by the 0.03, and I get 0.4 meters per second. The magnitude of the average force, the change in momentum over the change in time, so if it changes its momentum 0.096, and it does it in 20 milliseconds, then you have 0.096 over 20 times 10 to the negative 3, 4.8 newtons. State and explain whether the collision is elastic or inelastic. Because the speed of separation is 0.4, but the speed of approach was 2.8, we know that it is inelastic. Because the relative speed of approach, 2.8, is not equal to the relative speed of separation, which was 0.4. In practice, frictional effects are significant so that the actual increase in kinetic energy of the ball in moving from A to B is 76 millijoules. The length of the track between A and B is 0.6 meters. Use your answer in A to determine the average frictional force acting on the ball as it moves from A to B. So remember that our answer in A was the 0.09 joules. That was the gravitational potential energy. It says the actual increase in kinetic energy of the ball is 76 millijoules. So it's actually 76 by 10 to the negative 3 joules. So that's 0.076. So there we're sort of, we budget a theoretical energy of 0.09, but in actuality it's 0.076. And so how much energy are we missing here? 0.09 minus 0.076. We're missing 0.014 joules of energy. That's unaccounted for. The frictional force does work to slow it down. And so work is force times displacement. So the work is the sort of the work done by friction is equal to the energy that's missing, right? That energy is sort of lost as heat. So when you do the subtraction, what we're really getting is like the energy lost as heat from friction. So that energy is the work done by friction at every 0.6 meters of that track, right? Friction was acting. And so they're asking us for the frictional force, that's this. We just need to divide each side by the displacement, 0.6 meters, right? So that's what S is. So 0.014 divided by 0.6 gives us 0.02 newtons, 0.023 per rpm. State the two conditions for an object to be in equilibrium. So there can be no net force and there's no net torque. No net force, no net torque, or no moment. Those are the two conditions for equilibrium. A uniform beam AC is attached to a vertical wall at end A. The beam is held horizontal by a rigid bar BD. As shown in the figure, the beam is of length 0.4, weight W, empty bucket, weight 12, suspended by a light metal wire from the end C. The bar exerts a force on the beam of 33 newtons at 52 degrees to the horizontal. The beam is in equilibrium. Calculate the vertical component of force exerted by the bar on the beam. So I think we want this force right here, right? The vertical component of this force. So that's the same thing as like right here. If we looked at this triangle and we said, I know 52 degrees, I know 33 hypotenuse, and I want to know the side opposite that 52-degree angle, then I guess a straightforward way to solve this would be the sine of 52 degrees would equal the opposite, right? The thing I want to know, the vertical component. So let's call that the force vertical over the hypotenuse, which is 33 newtons. And so the force vertical is just going to be 33 newtons times sine 52. .26 newtons. By taking moments about A, calculate the weight W of the beam. So now we need to get this one. All right, so if there is a force of 26 newtons acting 0.3 meters away, that's going to be a anti-clockwise moment, but there's a clockwise moment from this 12 Newton force acting 0.4 meters away. So we have a clockwise moment, we got an anti-clockwise moment, this would be another clockwise moment. So 26 newtons times 0.3 meters. So this sort of moment here is the anti-clockwise moment equals 26 newtons times 0.3 meters is 7.8 Newton meters. The clockwise moment that we know about is the 12 Newton weight bucket acting 0.4 meters away. So 12 times 0.4, that's 4.8 Newton meters. So for this thing to be in equilibrium, we need these to be the same. And so we're missing 3 Newton meters of clockwise moment. And so all that must be provided by the weight of the beam itself, because it's acting clockwise. And so because it's uniform, it's acting 0.2 meters away. So basically we're missing 3 Newton meters of moment. And we know that it's from the weight that's acting 0.2 meters away. So 3 divided by 0.2 is 15 newtons. We'll call it a day there.